day everyone! In this video, I will be discussing one of the theorems under Math 822A Foundations of Mathematics. I am Jamari May A. Latrop, Mame 1. This theorem is under Chapter 14, which is about cardinal numbers, found in the book Foundations of Mathematics by Ian Stewart and David Todd. In this video, I will be discussing about the Schroder-Berstein theorem. This theorem is a result from set theory. It is named after Ernst Schroder and Felix Bernstein. Friedrich Wilhelm Karl Ernst Schroder made original contributions to algebra, set theory, lattice theory, ordered sets, and ordinal numbers. While Felix Bernstein established his famous theorem on the equivalence of sets while in Cantor's seminar at Halle in 1897, he also worked on transfinite ordinal numbers. This theorem is also known as Cantor-Schroder-Bernstein theorem, named after George Cantor, who first published it without proof. So what is this theorem about? In set theory, let A and B be sets. If there exist injections F from A to B and G from B to A, then there exists a bijection H from A to B. Another way to state this theorem is in terms of cardinality of two sets. So given sets A and B, if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then cardinality of A is equal to the cardinality of B. This theorem can be used to solve many cardinal arithmetic problems. The result is extremely useful in set theory when you are trying to prove that two sets have the same size, because it allows you to do so by establishing an injection each way as opposed to explicitly constructing a bijection between the two sets, and that's often much easier. Before diving in with the proof, I will first give you an example that will help you gain insight about the theorem. So this example is by David Hilbert, known as the Hilbert's Hotel. He used the example of a hotel to demonstrate the counterintuitive games you can play with infinity. Suppose you're a hotel manager and your hotel is full. That's great, of course, but there's always the temptation to squeeze in more guests. In real life, this might mean clearing out the broom cupboards and getting bad reviews about your hotel. But in the world of maths, it's no problem. Now, suppose that Hilbert's Hotel has infinitely many rooms, numbered 1, 2, 3, and so on. All rooms are occupied. When a new guest arrives and asks to be put up, what do? Can we accommodate the guest the same way? Meaning, can we accommodate the new guest in such a way that all the guests, old or new, are occupying exactly one room? The answer is yes. To accommodate a new guest, simply move the guest in room N to room N plus 1 and put the new guest in room 1. We do this simultaneously for all guests. So guest currently in room 1 goes to room 2, the guest currently in room 2 goes to room 3, and so on. And then we put up the new guest in recently vacated room, which is room number 1. Once that's done, we accommodated all of the guests, both old and new. Now, suppose that countably infinitely many new guests arrive and want rooms. Can we accommodate all of these new guests? Again, the answer is yes. So to accommodate countably infinitely many new guests, we move the guest in room N to room 2N and put the new guest in rooms 2N minus 1. So this means that we're taking the guest currently in room 1 to room 2, the guest currently in room 2 to room 4, and so on. In other words, moving all of the existing guests into the even-numbered rooms, and then putting the new guests into the recently vacant odd-numbered rooms. So the new guest 1 goes to room 1, new guest 2 goes to room 3, and so on. So you can keep iterating this, and you can prove that you can actually accommodate even an infinite sets of infinitely many new guests. We can use this idea to prove the theorem. So again, we have injections F from A to B and G from B to A. We can use F to pass from A to B or G to pass from B to A. Repeating the process, we can pass to and fro obtaining F of A, G F of A, and so on. To draw connection between the Hilbert's hotel room example and the Schroder-Berstein theorem, I'm going to draw the sets in the theorem as lines. The points in the set are the points in the line, and the arrows indicate the mapping G from B into A. Let us assume that the points in A are the guests, points in B are the rooms in the hotel, and G are the guests currently occupying the given room. As we can see, all of the rooms in B are mapped in this part of A on the right, while this part of the A is not mapped into. These are the guests that don't currently have rooms. Recall that what we're trying to do is to construct a bijection from A to B. So essentially, what we are trying to do is to accommodate all of the guests, both the guests that currently have rooms and the ones that don't currently have rooms, and find rooms for all of them. We need that each guest is mapped to a distinct room, so we should never have two guests pair up in the same room. And we need that all of the rooms are occupied when we are done. Let us represent the guest in this part of A as A0 or A sub 0, defined to be the set of all points in A that are not in the image of B under G. These are the guests that don't currently have rooms, and we're gonna try to find these guest rooms, and the way we're gonna do it is using F. So we can use F to indicate the rooms to which we would like to map this guest. We can't just put them into those rooms because we have guests occupying those rooms, and we can see which guests those are by applying G to that image set of A not under F. When we apply G, we see that A sub 1, which is defined to be G of F of A0. This set, A sub 1, is the set of guests currently occupying the rooms where we would like to put the people in A sub 0. So in order to accommodate the guest in A sub 0, we are going to shift or move the guest in A sub 1 down to the new room using F. This is similar to the Hilbert's hotel room example, where we are going to move the guest down by one room, except here we are moving sets of guests, possibly infinitely many guests, using F. We keep repeating this infinitely many times, so A sub 0 gets mapped by F that's displaced by A sub 1, which will then displace another set of guests, and so on infinitely many times. Formally, let A sub 0 is A minus G of B, which are the set of points in A not in the image of B and G. Next, A sub n plus 1 is equal to G of F of A sub n. In other words, to get A sub n plus 1 from A sub n, you apply F and then you apply G to the result, just like what we did in the diagram, to get from A sub 0 to A sub 1. Finally, A infinity is equal to the union of all the ANs, so this is all of the guests that are new as well as the guests who were displaced in this process. Now, we can define our mapping. So we define H from A to B by H of x is equal to f of x if x is an element of A infinity, and G inverse of x otherwise. So our claim is that H is a bijection. For injectivity, we must show that h of x is equal to h of y, and this implies x is equal to y. So we have the following cases. First, if x and y is an element of A infinity, so by injectivity of f, because when x and y are A infinity, h is just defined in terms of f. Second, if x and y are not elements of A infinity, then by injectivity of g, since the injectivity of g implies the injectivity of g inverse. For the last case, we have if x is an element of A infinity but y is not an element of A infinity. This is for x is an element of an for some n. So by definition of h, if h of x is equal to h of y, that means f of x is equal to the g inverse of y. Again, this is from the definition of h applied to x and y. But if that's the case, then we can apply g to both sides of the equation to get y is equal to g of f of x, which is an element of g of f of a sub n. Since x is in a sub n, but that said is just a sub n plus 1, so by definition, this tells us that y is in a sub n plus 1. But this is a contradiction because we are assuming that y is not in A infinity. Therefore, h is injective. Now, relating this to the hotel, this means that this mapping shows that the hotel never sends two guests in the same room, meaning each guest is mapped to a distinct room. Next, for surjectivity, we must show that for each z is an element of B, there exists x, which is an element of A, with h of x is equal to z. In other words, this mapping shows that each room has a guest. Now, consider that x is equal to g of z. So we have the following cases. First is if x is not an element of A infinity, then we can say that h of x is equal to g inverse of x is equal to z. This is by the definition of h of x. Second, what if x is an element of A infinity? Then x is also an element of A sub n for some n. We must have that n is greater than 0 since x is an element of g of b. So, therefore, x is an element of g of f of A sub n minus 1. That is, x is equal to g of f of x prime for some x prime is an element of A sub n minus 1. Now, this means that z is equal to the inverse of g of x, which is also equal to f of x prime and equal to h of x prime. Therefore, h is surjective, hence bijective as claimed. Let us observe the given example. We will use the Schroder-Berstein theorem to show that the sets 0, union 2 and infinity, and 1 and 2 are equivalent. So we must establish that there is an injection f from the sets 0, union 2 and infinity to 1 and 2. So let us define f of x as 1 when x is equal to 0 and 1 plus 1/2 when x is an element of 2 and infinity. Then by definition, we can say that f is 1 to 1. Next, let us define g of x. So g of x is 0 if x is equal to 1, and it is x plus 1 if x is an element of the set 1 and 2. Then we can say that the relation g from 1 and 2 to the set 0, union 2 and infinity is also 1 to 1. Now by Schroder-Berstein theorem, we can say that f is a bijection between the sets 0, union 2, infinity to 1 and 2. Therefore, the set 0, union 2 and infinity is equivalent to the set 1 and 2. This is the end of my presentation. Thank you.